we now discuss the solution of a problem from the section Algebra, and the problem is from the group theory. This question has appeared in CSIR National Eligibility Test held on 30th November 2020, and it is from the section B. The problem is, let G be a group of order 2020. Which of the following statements is necessarily true? The four options are given to us. Option 1, G is not a simple group. Option 2, G has exactly 4 proper subgroups. Option 3, G is a cyclic group. Option 4, G is abelian. Let's now first of all review some of the results from group theory based on Sylow's theorems. Let P be a prime number. Order of G is equal to P power R into M, where P does not divide M. Then the first result is G has a subgroup of order P power R henceforth called P Sylow subgroup, in short PSSG. And we have a famous theorem, that is the third Sylow theorem. It states that the number n suffix p of P Sylow subgroups of G is given by NP is congruent to 1 mod P, that is NP is equal to 1 plus Kp, where K is equal to 0, 1, 2, etc. and NP divides M. And we have another result. A P Sylow subgroup of a finite group G is a normal subgroup of G if and only if it is the only P Sylow subgroup of G. If it is the only P Sylow subgroup of order G, then it is a normal subgroup of G. We have the definition for simple group, and a group G is said to be simple if it has no proper non-trivial normal subgroups. Solution. We have the group G and the order of G is 2020. Let's now discuss the validity of the statement that is given in the option 1, which states G is not a simple group. Let's now take the prime factorization of the order of G. Order of G is equal to 2020. The prime factorization is 2 square into 5 into 101. This implies by the first result, G has a P Sylow subgroups for each P is equal to 2, 5, 101 of order 2 square, 5, 101 respectively. Now order of G is equal to 101 into M, where 101 does not divide M, where M is 2 square into 5. Then we apply Sylow third theorem. Then NP, N101, that is the number of P Sylow subgroups of G, is given by NP is congruent to 1 mod P, that is N101 is equal to 1 plus Kp, 1 plus 101 K, where K takes the values 0, 1, 2, etc. and N101 divides M, where M is 2 square into 5. This implies 1 plus 101 K divides 20. This implies k is equal to 0. This is valid for the value k is equal to 0, and thereby n101 is equal to 1. This implies G has only one p silo subgroup. Let's call this as the H for p is equal to 101. So H is a normal subgroup of order p is equal to 101 of G. Why? Because it is the only one p silo subgroup of G. So this implies G is not a simple group because it has a non-trivial normal subgroup H of order 101. G is not a simple group, so which the statement that is given in option 1 is true. So therefore the option 1 is true. And because this is a problem from the section B where only one answer is true, our answer is option 1. However, we will discuss the other 3 statements also, and we will give a counter example for those 3 statements to say they are not true. Let's first review the results on dihedral groups. For n is equal to 3, 4, 5, we define nth dihedral group, that is the group of symmetries of a regular n-gun, and the nth dihedral group is denoted by Dn, and it is of order 2 into n. A regular n-gun has 2n different symmetries, and it has n rotational symmetries and n reflection symmetries. In total, it has 2n different symmetries. Dn is generated by a rotation rho of order n and a reflection mu of order 2. Every reflection is of order 2 such that rho mu is equal to mu into rho inverse. So the Dn is described as that it is generated by 2 generators rho and mu, whose defining relations are rho power n is equal to mu square is equal to identity, rho mu is equal to mu rho inverse. And note down the nth dihedral group Dn for n greater than or equal to 3 is non-abelian. Why? Because rho mu is equal to mu rho inverse, which is not equal to mu rho. So the nth dihedral group for n greater than or equal to 3 is always non-abelian. Now let's take down the statements that are given in options 2, 3 and 4. Let G is equal to Dn, the nth dihedral group, that is the groups of symmetries of a regular n-gun, for n is equal to 1010, and thereby the order of G will be 2n, that is 2020. And we have, in the review we have seen it has n is equal to 1010 reflection symmetries, and each reflection symmetry generates a cyclic subgroup of order 2. So thus in this case it has n is equal to 1010 cyclic subgroups of order 2. So thus G has more than 4 proper subgroups. Thereby the option 2 is not true. Option 2 says it has exactly 4 proper subgroups. So the option 2 is not true. G is equal to Dn is a non-abelian group for n greater than or equal to 3. Since Dn is generated by a rotation rho of order n and a reflection mu of order 2, such that rho mu is equal to mu rho inverse. Because it is non-abelian, it is not a cyclic group. Therefore, G is equal to Dn is not a cyclic group. Therefore, the option 3, that is, it is a cyclic group, is not true. Option 4, that it is G is abelian, is not true. So thus the options 3 and 4 are not true. Therefore, our answer is option 1 is true. So that is an interesting problem from the group theory. And I am sure that you have understood the solution of this problem, and go on working out some more problems on the applications of Sylow's theorems. I wish you all the best. Thank you.